Okay, so in this section we'll be talking about the Laplace transform. So let f be a function defined for t greater than 0 or equal to 0. The integral L of f, defined to be this integral from 0 to infinity e to the minus st f of t dt, is called the Laplace transform of f, provided that the integral converges. And convention, we use capital F of s to denote the Laplace also. So sometimes we'll use capital F of s to denote this Laplace transform. Okay, so let's take a look at a theorem. Okay, so theorem 13, we have to show the Laplace transform of e to the at we need to prove is equal to 1 over s minus a. So let's use our definition of Laplace transform now, with our f being e to the at. So let me write it here. Okay, so I'm going to apply the definition of Laplace transform with my f being e to the at. It's going to be integral 0 to infinity, which you have here, e to the negative st, which you have here, times my f. Well, my f this time is e to the at dt. Okay, so I need to integrate this. So let's add the exponents there. And also, since we're integrating to infinity, we're going to have to write this as limit in front here. B goes to infinity, and replace the infinity up here with the b, because it's an improper integral. So I'm going to write it here. Okay, so rewriting the improper integral, because it's going to infinity on one of the limits here, as limit b goes to infinity and then b up here, and then adding the exponents, which I've done up here. Then I've factored out a t, so I can write it this way. And then we can integrate this then. So integrating, we get then. Okay, so when I integrate e to the a minus st, it's going to be 1 over a minus s e to the a minus st. And the reason is, recall up here, if you integrate e to the kt, it's just going to be e to the kt over k, where k here is a constant, say, plus some c. Okay, so here my k would be the a minus s. Okay, so now I'm going to plug in b in place of my t and 0 in place of my t. So doing that, I get then. Okay, so putting b in place of my t first, and then putting 0 in place of my t. Okay, and now we have to, so this will be e to the 0 here, which is just 1, this part, and we have to try and figure out what this is over here. Actually, we're going to have to make an assumption here. I probably should have wrote it at the beginning. We're going to assume that s is greater than a. So let me write it up here now. Okay, so I should have wrote this at the beginning of the theorem. So this is true when s is greater than a. Okay, so we need to then make an observation here. Since s is bigger than a, it means that a minus s is negative. But I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's where we left off. We had our Laplace of e to the at equals limit b goes to infinity of e to the a minus sb over a minus s minus, it was e to the 0 here, but e to the 0 is 1, so it'll be 1 over a minus s. And we added the condition that s is greater than a. So note then, s greater than a means that a minus s is less than 0, and a minus s times b, if b goes to infinity, since a minus s is negative, would mean that this is going to negative infinity. Okay, so let's keep going then. So therefore this will be e to the minus infinity up here. That's like 1 over e to infinity, which is going to be 0. So let's write that here. So note then, limit b goes to infinity of e to the a minus s times b. Well, as we mentioned, the a minus s is negative, and we mentioned this guy is negative infinity. Therefore, it's going to be e to the negative infinity, which means 1 over e to infinity. And 1 over this is pretty much 1 over infinity here, but 1 over infinity is 0. Okay, so this part up here then will be 0, and it'll be just left with this guy here, so it's right here. Okay, so since this guy is 0, it means this part up here will be 0. So my Laplace transform then of e to the at will be 0 minus 1 over a minus s. But that minus sign you can bring to the bottom and multiply it in. It'll become then 1 over s minus a. And that's what we're trying to show. So we're done with the proof. Okay, so I'm going to leave it there in this video. We'll continue in the next video with more properties of the Laplace transform. So let's leave it there.